Uh, Hello everyone, this is Zahid Bashir, your trainer for Quantitative Primary Data Analysis. And previously we have discussed about uh, different cases of regression in which I have discussed with you first four cases. And I have given the brief overview how these cases can be discussed with reference to SPSS analysis. And in my yesterday session, I have I have let you know about how to conduct the simple regression analysis when you have a quantitative uh, independent variable as well as all right uh, when you need to do a quantitative um, when you need to use the quantitative independent variable and a quantitative dependent variable, this is a simple regression case. That was the case one that we have previously discussed yesterday. Then, in case of second regression case, there might be more than one independent variable with a quantitative nature, and your dependent variable would also be a quantitative one. So that was the second case that we have discussed. Then we discussed the third case where we run the simple regression analysis with binary independent variable. For example, we have taken gender as our independent variable, and we have analyzed the impact of gender on our quantitative dependent variable. Then we have discussed the fourth case, which is simple regression analysis. In this case, we have discussed more than two categories in our independent variable. And if you know my previous lecture, and if you attended that lecture, I also let you know that how to create the dummy variable when you have more than two categories. In this case, in case number four, we have created dummy variables and we have run their impact on our dependent variable, which is quantitative. So today we will discuss how to analyze binary logistic regression. So case number five, case number six, and case number seven are related with binary logistic regression, where your independent variable might change, but your dependent variable remains same. So in case of binary logistic regression, the dependent variable would be binary. It means two options would be provided with 0 and 1 coding. So your dependent variable would be binary, but your independent variable will be changed. So in case number five, your independent variable would be quantitative. In case number six, your independent variable would be binary. So in case number six, your dependent and independent both would be binary. And in case number seven, you may have an independent variable with more than two categories. That is categorical variable. So your DB would be binary, but your IV would be categorical. So first we analyze these three cases, then we go to the advanced version, which is multinomial logistic regression, where we also analyze that our dependent variable having more than two categories, but independent variable will change. The first would be quantitative, then we will use binary, then we will use categorical. So in case of multinomial regression, your dependent variable might have more than two categories. But in case of binary logistics, your dependent variable might have two categories. So let's start how we can analyze from case 5, because we have discussed up to case number 4 yesterday. So I will go directly to case number 5 because we have discussed up to case number 4 yesterday. You can see the recordings if you have missed case number 4. It was the last one case that I have discussed. So we have to start from this case, case number 5. This is basically the today's case number 5. So we will start from here. So in case number five, your independent variable would be quantitative. It means it would be measure either interval scale or ratio scale, while your dependent variable would be binary. So what you need to do, I have designed some steps that you would analyze while doing your analysis of logistic regression. So let's suppose we need to analyze a situation where we want to know that is there any effect of age on status of heart disease. Here the age is quantitative variable because we are dealing with the quantity, while heart disease might be binary. Status of heart disease, either the person is getting the heart disease or not. So your dependent variable is binary, your independent variable, which is age, is quantitative. So how we will establish our hypothesis, our null hypothesis would be there is no effect of age on status of heart disease, while our alternative hypothesis would be there is an effect of age on status of the heart disease. So when your DV becomes binary, it does not matter what is your ID. It will require logistic regression. Step one. This whole process requires basically three steps, and I would request you to please uh, understand these three steps because following these steps will make you clear about binary logistic regression. So if you want to learn, if you are learning the binary logistic regression for the first time and you are not aware with it, or you have not previously learned about it, you need to understand these three steps. And I will analyze my data set according to these three steps. The first step is that you need to run the binary logistic regression with DV, that is status of heart disease that we have previously discussed, and our IV as a age. And we need to establish a predictive regression model. I will let you know how we will establish a predictive regression model using the first step. Then in the second step, we will calculate some values like Z distribution of predictive model. Then we will calculate negative Z. Then we will calculate exponent of negative Z. Then we will calculate 1 plus exponent of negative Z. Then we will calculate the probability of heart disease, which is our dependent variable. We need to calculate its probability in the fifth phase of our second step. So that is basically 1 divided by exponent of negative z. So how I will let you know. Then after calculating your probability of heart disease, you will go towards the step 3, which is creating scatter plot for probability of heart disease. So in this example, we will analyze our data using binary logistic regression. And how can we understand that binary logistic regression is required? Whenever your dependent variable is under the shape of binary, you need to understand that your DV requires the binary logistics. So when your DV becomes binary, it does not matter what is your ID. It will require binary logistic regression. So let's analyze our data. So first, I will let you know the whole process. How can we apply this process? First, we need to analyze our binary logistic regression. So how can we do it? We can go to the analyze then regression, and then we will select binary logistic as an option. So after selecting it, because we are applying the first step, so what will we do next? We will put our dependent variable in dependent list, and we will put our independent variable in the covariate list, and we will click on the OK button. So after clicking the OK button, you will get these results. You can see here, you need to ignore the block 0 results because it will generate two blocks of your regression results, block 0 and block 1. For the purpose of binary logistic regression, we need to see the block 1 method. We need to ignore the block 0. So we need to see the results under block 1. So what will you see? You will see the omnibus test of model coefficient. It will let you know whether your model is statistically fit or not. So sig value is 0.05, reject H naught. And what we conclude here, if this value is less than 0.05, it means that you are rejecting the H naught and your model is statistically fit. So what we can conclude here, we can conclude that there is an impact of age on status of heart disease. So you can also analyze the model summary, and you need to see the value of Cox and Snell R square. You can see here the value of Cox and R square, Cox and Snell R square is 25%, 25.4%. And what this value indicates, this value indicates that the variation of the status of heart disease is 25.4% is explained by the variation in age. So this is how we can do this interpretation. But there are two more tables that we need to understand. There is a classification table which is generated as a part of the binary logistic regression, and there is also a variable in the equation. So how can we interpret both of these tables? The classification table actually represents the predictive accuracy of the model, whether your model is accurately predicted or not, where you can find three different values in percentage correct column. The first value represent basically the prediction of negative instances. The second value indicates the prediction of positive instances, while the third value indicates the overall percentage of correct prediction. It means our model is 74% predicting accurately our results. So our prediction is 74%. Our correct prediction is about 74%. I will let you know in detail about this table in a Word file, and you will understand the whole scenario. Then you will need to understand the variable in equation table. You will see a sig value which is less than 0.05. So what it indicates? It indicates the H naught is rejected, and your H naught was that there is no impact of your independent variable on your dependent variable. So as the sig value is less than 0.05, so we can conclude that H naught is rejected and H1 is accepted. So there is an effect of age on heart disease status. With 1 year increase in the age, there is 1.117 times chance of having a heart disease. This is basically the interpretation of binary logistic regression result. But what we will do with this beta value, we will create a predictive model using these beta values. So use these coefficient value for your predictive regression model. So we will put the constant value first, and then we will put our age in years value secondly. And this is how the predictive model is created. You just need to put your constant first, and then a plus sign, and then your independent variable coefficient value. So this is basically the step one. This is the completion of your step one. So I will analyze this whole procedure using binary logistic regression. So what data we are going to analyze? We are basically dealing with case number 5 data. So let me show you how this could be done using our data set over here. I have shared data set with you yesterday, and this is case number 5 data. You need to open case number 5 data, and you will see the data set like this. First of all, you need to remove z, negative z, exponent z, 1 exponent z, and phd. You need to remove these four. You need to keep age and status, but you need to remove the remaining four. So I will remove them. and let's suppose we have this data set. So we need to analyze that our dependent variable is the status of heart disease, which is binary variable. You can see the value of 0 and 1. So in case of binary logistic regression, your dependent variable would be binary. So here it is a binary variable, while your independent variable is basically quantitative because it is measured in scale. So as a first step, what we will need to do, I have previously explained to you that you need to run the binary logistic regression. DV is status of heart disease and IV is age, and establish a predictive regression model. So how can we do it? We just simply need to go to analyze, then we go to regression, then we go to binary logistic. That is basically the binary logistic. And why we are using it? Because our dependent variable is in binary shape. So we will select it and we will put our dependent variable, that is heart disease status. Here it is indicated as a status, but actually it is heart disease status. So we need to put it in the dependent variable, and we need to put age in the covariate. We don't need to do anything over here further. We just need to select OK, and we will see the results like this. As I have previously told you that you need to ignore the block 0 results. You need to ignore the block 0 results and you go straight to the block 1 results. So here you can see the block 1 results. First is the omnibus test of model classification. There was an interruption of internet, so I am again sharing. I was letting you know that after getting the results, you need to see the results under block 1. So at first, omnibus test of model coefficient will let you know that whether your model is statistically fit or not. So here it indicates that model is statistically fit, and it also indicates that there is an impact of age on heart disease status. So whenever your model is showing a sig value less than 0.05, it means your independent variable is impacting your dependent variable. So next we need to see the model summary. Here we need to interpret the Cox and Snell R square. So it is indicating that your dependent variable is explained 25.4% variation by your independent variable. Uh, and what was your dependent variable? Your dependent variable was heart disease status. So we can say that heart disease status is 25.4% is explained by age, and age is basically our independent variable. So this is how we can interpret it. Then we can see the classification table. In the classification table, you need to concentrate on the last value. That is the overall percentage. And it indicates that our predictive model is 74% correctly predicting our model. So this table indicates that our model is correctly predicting about 74% of our data or our prediction. So next is the variable equation. Here you need to see first of all the second last column, that is the sig value column. So it indicates that uh, your sig value is less than 0.05. So it means that there is an impact of your independent variable on your dependent variable. Your independent variable is basically the age, and your dependent variable is basically the heart disease status. So we can say that there is an impact of age on heart disease status, and this impact is positive. If you can see the beta value and exponent b value, this impact is positive. So whenever the age increase, the probability of occurring the heart disease is 1.117. So I have also interpret this table over here. You can see whenever there is an effect of age on heart disease status with 1 year increase in age, there is a 1.117 times chance of having a heart disease. So this is how you interpret your binary logistic. But this is not completed over here. We need to establish our model are basically predictive model. So how can we establish that predictive model? Here is the constant value. You need to put this value as a sum of the age beta value, and your predictive model will be established. So your predictive model will look like this. So you need to add the constant value first, then you place a plus sign here, then you need to put your coefficient of age and then x. So this will be basically used in our second step. So I think you have cleared about the first step, but as I have told you, I will let you know about the classification table in more detail. So first, I would like to let you know what is basically the classification table and what it is indicating. I have thorough work on classification table, and I would like to explain you in more detail that how it can give you an idea about what different values are. You can see in the classification table there are four values. Uh, with no and no, 45 values are indicating. With yes and yes, 29 values are indicating. With no yes, 12 values are indicating, and with yes and no, 14 values are indicating. So we can say 45 is indicating no and no. So what does it mean? What does it mean? What is 45 indicating over here? 45 is indicating the true negative. So if a value is true negative from vertical side and as well as on the horizontal side, it is true negative value. So what does it mean? It means that 45 cases where the model correctly predicted no. So when there is a correct prediction, uh, what is the correct prediction? It means no heart disease when the actual status was no. So when a person having no heart disease and he is not getting any heart attack, it means there are 45 cases where a person is neither having a heart disease and he is not getting any heart attack. So this is true no cases. This is true no cases. This is TN. Then you go to the yes. Yes from the vertical side and yes from the horizontal side. That is 29. It is true positive case. It means if a person is having a heart disease and he is getting the heart attacks. So if a person is having a heart disease and he is getting the heart attacks, so it is considered a true positive case. So there are 29 cases where a person having a heart disease and he is also getting heart attacks. Next, if you can see the false positive, what does it mean? False positive means when you have a heart attack status no, but you are getting the heart attack. So there are 12 cases where the model incorrectly predicted. It means that a person does not have a heart disease, but he is getting the heart attack. So it means you have not predicted correctly. You cannot predict. You have predicted that if a person is not having a heart disease, he will not get a heart attack. But in this case, the predictions makes us wrong. So we can say there are 12 cases where a person does not have a heart disease, but he is getting a heart attack. So this is basically the false positive case. And there are some cases where a person having the heart disease, but he's not getting the heart attack. So this is false negative case. 14 cases where the model incorrectly predicted. This is also called the incorrect prediction. So in this case, the person is not having the, the person is not having any heart attack, but he is having the heart disease. So this is how we can interpret it. So how can we interpret these three values? There is a criteria that I would like to let you know. This is basically the criteria. In case of overall accuracy, you need to consider true positive plus true negative divided by true positive, true negative plus false positive, false negative. So when you analyze these numbers, it will give you 74%. That is already there. You can see this value here. This is 74%. It means we are our model is or our model's correct prediction power is 74%. So we can say that in our case, the model is overall the model is correctly predicting our results or our model. This value should be greater than 50%. If it is less than 50%, it means your model is not correctly making the prediction. But in our case, it is greater than 50%. So we can conclude that our model is correctly predicting our result. So this was how you can understand different values in your classification table, but you don't need to interpret in detail, in thorough detail, as I have told you. You just need to interpret the only one value from this table, that is your overall percentage. If this value is greater than 50, it means your model is correctly predicting, the overall your model is correctly predicting. So you need to see only, you need to focus on this value. So let's go for the second step. When you have completed the first step, you need to go to the second step, which is a thorough step, and you need to understand this step in more detail. As I have told you, that as a first step, you need to run the binary logistic regression, and we have run it and we have interpreted it accordingly. Then we need to establish a predictive regression model, and we have established our predictive regression model. As a second step, you need to analyze some more phases uh, using your predictive model. So you need to create z distribution of your predictive model. Then you need to create the negative z. Then you need to create the exponent of negative z. Then you will create 1 plus exponent of negative z. Then you will create a reciprocal, which is 1 divided by exponent of z. So you can see that each of the steps require some preliminary steps. So if we need to create probability of heart disease, we need we will be needing to complete all these steps. So after completing this step, you can create a scatter plot of probability of heart disease, which is basically the final step in binary logistics. So let's start these steps. Starting these steps, we would require a predictive model that we have calculated over here. You can see in our slide, I have told you that in our case, our predictive model, what would be our predictive model? I have told you that as a last step, you need to analyze your constant value of age and your coefficient value of age in order to use them in a predictive model. So how can you create a predictive model using these values? You can create the predictive model. Now I will analyze these results in order to create a z distribution. So how can we do it? Just go to the regression, and you need to go to the transform menu. Here there is a option of compute variable over here. You need to click it. You need to create z distribution of your predictive model. So in the target variable, you need to write z hyphen, to write the hyphen, not the dash, z distribution. And you need to put here your predictive model. So how can you put your predictive model over here? Here it is minus 5.309, which is the first part of your predictive model. Minus 5.309. So you need to write here minus 5.309. I think this was the value. Yes. Then you need to place a plus sign and 0.111, which is also indicating over there. Plus sign and 0.111. You need to use plus sign. Then what you need to do, you need to add the variable of age over here. So go there and you need to use the variable of age. You just simply double click, but before using the double click, you need to use a multiplication sign, because this value is basically multiplied with age. So you need to put an asterisk sign which is used as a multiplication. Then you need to double click the age variable over here. So just like this, you have created your Z distribution for your predictive model. You just need to click OK button, and you will find an additional column over here. Here it is. You can see the Z distribution has been created. You can also verify it in the data view. Here it is. So this is how your first phase of your second step has been initialized. So we have basically done the first phase of our predictive model Z distribution. The next phase is we need to create the negative Z. So how can we create it? You just go to the transform, you go to the compute. Every time whenever I am doing this, at first you need to reset it. How can you reset? You have a button in the bottom side. There is a reset button in the bottom side. You need to click it, and then you need to go again in the target variable. You need to create net and distribution, just like this. And you go to the equal sign numerical expression, and you need to put the negative sign over here, and then you double click the Z distribution. Double click. And you can see there is a negative sign with Z distribution that has appeared over here. So how I did this, I just write the name negative Z distribution with the hyphen between negative and Z distribution. Then I put in the numerical expression the minus sign from here, and then I double click the Z distribution which I have created in the previous step. You just need to click OK button after this, and you will see that you have that you have the value of negative z over here. So what difference you have noticed over here? The difference is the z distribution was showing the negative value for each of the values indicated over here, while the negative z, it is indicating the positive values. So if you see in the numerical variable view, you can see these values over here. So we have done the second phase of our step, of our second step, that is negative z. Then we need to create exponent of negative z, that is the third phase. So how can we do it? Again, we need to go to the transform button, then go to the compute variable. We need to reset, because every time we need to enter a next phase, we need to click the reset button. So you need to create what we require. We require basically